This podcast is sponsored by QCon AI, the Applied AI conference for software developers. Focusing on the practices of artificial intelligence and machine learning, QCon AI takes a different tack than most other major software conferences in the AI ML space today. Rather than focusing on data scientists, QCon AI targets how full stack software engineers can apply machine learning and AI techniques in their day-to-day roles. QCon AI takes place in San Francisco, April 9th through 11th, 2018. You can find out more about the conference online at qcon.ai.
Welcome to the InfoQ podcast. My name is Wes Rice and I'm your host. The InfoQ podcast is brought to you by InfoQ.com. Today on the InfoQ podcast, I'm talking to Tyler Akidau. Tyler is a senior staff engineer at Google. He leads the technical infrastructure's internal data processing teams in Seattle. He is a founding member of the Apache Beam PMC and a passionate voice in the streaming space. In this podcast, we talk about streaming, data streaming. We focus heavily on the 2015 data flow model paper that he was the primary author on, and much of the concepts that the paper surfaced, including why dealing with out-of-order data is important, event time versus processing time, windowing approaches, and then we finally wrap up with previewing the QCon SF track that he's hosting just around the corner on November 13th through 15th at QCon SF. Thanks for listening. I hope you enjoyed the podcast. Tyler, welcome to the InfoQ podcast.
Thanks for having me.
So last November, you did a talk at QCon SF around the fundamentals of stream processing with Apache Beam. In that talk, you discussed Apache Beam as an incubating project. In January of this year, it graduated, right?
Technically December.
So what does that mean to be graduated now for Beam?
So it means that Beam is a full-fledged top-level project. Incubation is really, at least as I understand it, we're still relatively new to the community, but as I understand it, the goal with incubation in Apache is really to ensure that projects build up a thriving community and do so in the ways, sort of the Apache way, the way that's worked well for lots of their projects. And so it's, graduating to top level is really an indication that you've accomplished this. You've built a community that's not driven by a single company. It has lots of outside influence, lots of people collaborating, and it's done in a way that's open and truly community-driven.
How is that measured? How does Apache measure that you've got the community and the open source commitment? There's
a few things there. One is that they look at the distribution of committers, so they like to see that committers are not all from a single company. They also look at the distribution of commits, so you can imagine having committers that are from lots of different places, but all the commits coming from basically folks from one single company, things like that. They also look at user list and dev list interactions, and every incubating project has mentors associated with it, who are folks who are very deeply embedded in the Apache ecosystem, and they kind of have a pulse on things as well. So they read from that, and there's probably other things as well.
Let's kind of kick it off and start from the very beginning. I guess the very beginning for me, at least, and it probably isn't the very beginning, but I guess 2004 is when Google published the MapReduce paper, right?
Yes.
So that defined this kind of batch processing system. In the years since then, we've kind of moved into microbatch, we've moved into streaming, we moved into a variety of different ways. I guess Spark probably is the first thing that comes to mind, at least for me. What was the big challenges that Spark solved over the batch processing with Hadoop?
So talking about Spark streaming specifically then, because Spark solved a whole bunch of issues over Hadoop, but also in the batch realm. In the streaming realm, and this applies to streaming tools in general, Spark was definitely not the first on the scene, but the thing that the streaming tools really solved was giving you a way to build pipelines that could continuously process data over these unbounded data sets that are just continuously growing, right? And folks have been doing this for since 2004 and beyond with batch processing systems. It's just you had to break up your unbounded data sets into these finite data sets and then deal with them. And so having a natural way to express this over this continuous stream of data essentially is really the semantic change that these types of systems brought about.
Why was there this lack of trust with streaming systems? And I'm basically talking about architectures like Lambda architectures.
Right. So that came about because the early streaming systems essentially sacrificed correctness at some level in order to provide lower latency. That's kind of a nice way to trade those things off. And so as a result, what you ended up with was a set of streaming systems in the industry that couldn't be relied upon to give you absolutely correct answers or repeatable answers like you could with Hadoop. So you couldn't do things like build billing systems on them, for example. You're not going to charge people money when you aren't convinced that you're actually counting the numbers properly. And so this led to the Lambda architecture, where you would run a weakly consistent but low latency streaming system alongside a strongly consistent but high latency batch system, and kind of get both of the best of the both worlds. And that really was the biggest contribution that Spark Streaming initially had, was that they brought to the table a streaming system that also had with it strong consistency semantics.
In the data flow model paper, you and your co-authors talked about unbounded data and some of the way that teams at Google were reasoning about it. In your opinion, what was the big contribution of this paper to the community?
So I think there were two things, and these were actually highlighted by one of our VLDB reviewers. But I think the biggest overall contribution was that it gave a compelling and coherent picture for why dealing with out of order data was important, and sort of the fundamentals around it, and sort of the basics from which you could build systems that would actually support this kind of stuff. That was actually another aspect of the early streaming systems, was that they didn't really have, aside from the whole lack of strong consistency thing, which crippled them as far as being able to support this as well. But aside from that, they also didn't have a strong notion of event time, correct, sort of where things exist in event time, and how to deal with out of order data. So I think this paper really called that out in a clear way, showed, cited examples of why this is important, why we care about this, and why it's becoming increasingly important, especially in a world where mobile devices are so prevalent, and gave a clear, explanation for sort of the path forward. And that was kind of a call to action in some sense. So I think that's why the paper has been so well received. I think there are arguments to be made that there wasn't anything that was academically interesting in that as far as contribution goes. I think the main interesting academic contribution in the paper was the merging window support. So that allowed us to do dynamic windows, unaligned windows like sessions. But I think a lot of the impact just came from the clear message that it presented.
Yeah, I actually want to ask some questions here in just a minute about sessions and defining the bounds of sessions and things like that. Before we get into that, there's some terms that you used I want to just touch on because I think they're important to the discussion. It's event time and processing time. Can you do a quick kind of overview and kind of set kind of the vocabulary that we may be using over the next half hour or so for specifically timing?
Yeah. So really what we're talking about when we use these terms is defining specific points in time in the lifetime of a data record. So when you're analyzing data, particularly data that's generated by users, imagine that this data comes from some form of user interaction. So imagine you've got mobile phones, maybe you've got some new mobile game that your company's built, and users are interacting with it, killing orcs or crushing candy, whatever, generating scores, and you want to record when these things happen, and then later on you want to analyze these user events in the context of both when these interactions happen with your system and also in the context of when they happened with other people using the system. And to do that, you really want to utilize or be aware of the time when a specific event happened. This is the event time. This is when the user tapped the screen and created that score or launched some feature or whatever. But the important thing to realize here is that this is particularly in the case of mobile phones, but you get this with really any data source. The time when an event happens may be very different from the time when you actually see that event. And it's particularly exacerbated with mobile phones because a user can be using their phone, and it could be an offline airplane mode, for example. Maybe they're flying cross-Atlantic flight. So they're doing all this stuff on their phone, and the phone's dutifully logging it, making sure it's keeping track of everything that happens so that you can analyze it later. But your system won't get those events until they actually land, get off the plane, and turn off airplane mode. And so when the system actually sees those events, that's processing time, the time at which the records are being processed. And so, historically, a lot of systems didn't really provide primitives that allowed you to reason about these two. And so folks would, try to group up records by the time that the system saw them. And as long as records are all arriving roughly in order, roughly at, some consistent delta from when they occurred, you can kind of get away with this and it looks roughly right. But when you start introducing things like mobile phones into the equation, when you start having large-scale distributed systems that sometimes have network partitions, or maybe they're sort of multi-data center, multi-cluster type systems where you can have massive network delays or fiber cuts, things like that, you start getting to the point where you can have grossly inaccurate results if you rely on processing time as the sort of the dimension that you reason about the relation of events and time. And so what you really want to use is event time, that original marker of when an event happened, and put events into context using that.
So this is really what you mean when you say complete, right? So for the completeness means all the transactions that you're measuring have occurred.
So completeness is, I would say, an additional step beyond just that. So event time sort of tells you the actual point in time that a record occurred, and then this notion of completeness is giving you a sense of not only am I seeing events, where they actually occurred in event time, but I also have a sense for I've seen all of the events up to a given point in time. And this gets into the concept of watermarks, which is discussed in the paper and various blog posts. But really the idea is, if events can arrive out of order, then you need some other way of knowing, when have I seen all the events? Say up till noon. I want to process data in hourly windows, which means I want 10 to 11, and then an hourly window from 11 to 12. When I want to process that hourly window of 11 to 12, I don't want to do so, or at least I don't want to claim that the results that I calculate from that are complete and correct until I know that I've seen all the inputs that have event times up to 12. So that's what watermarks try to give you.
So I get the general conceptual idea of watermark, that it's like a guarantee that all this input has been observed, but how do you guarantee that somebody's not in airplane mode?
I mean, the short answer is you don't. The mobile case is the really tricky case. So watermarks are really very data source specific. So they're very, you build them specifically based off of the underlying architecture of whatever system you're using to consume the data. So say Kafka or Google PubSub or HDFS or whatever. Each of these have different characteristics that give you different abilities to reason about completeness. And then that's combined with the nature of the input source itself. For example, there's a vast difference between mobile phones, which you just simply cannot reason about completeness in an absolute way. Like you can't absolutely know that all of your users have given you all the data they're ever going to, versus say web front ends. So if you've got 100 web front ends serving your website and they're all logging to 100 static partitions in Kafka, you have absolute knowledge of everybody that's generating events. And if those web front ends are writing events sort of at real time, so you're assigning timestamps essentially as they're written to the log, you can build up an absolute perfect watermark over that sort of input source, because you have full knowledge of the input sources. You can, you've got a static set of partitions, each of which has monotonically increasing event times. You can essentially just monitor the distribution of event times across those static partitions, and the minimum is going to be your watermark. Whereas with something like mobile events, let's make it even worse and shove it into a system like Google PubSub, which doesn't give you real strong ordering guarantees. Like they try to give you ordering, but it's such an elastically scalable system that there's no actual guarantees there. What you end up having to do there, or what you end up trying to do typically, is build a heuristic that captures as much as you can of your knowledge of both the input sources and how the underlying transport works, and make a best guess. So like what we do for PubSub is we essentially track the timestamps of everything that's buffered in PubSub. And from that, we build a histogram that shows us what that distribution looks like. You take the minimum of that distribution. And as long as things are arriving roughly in order, you end up getting a relatively accurate heuristic watermark that tracks the completeness of things that are arriving in a timely fashion. And if something weird happens and you end up with a massive amount of data buffered in PubSub, the watermark will catch that and it will hold you back and say, no, you actually are missing a lot of input data. You shouldn't treat it as complete yet. It won't catch grossly late records. Somebody's on a flight for 12 hours and turns it on later, and so you can't use that type of watermark as I know for absolute sure that I will never have late records, but you can use it as I have a strong belief that I have most of my data.
Got it. Okay. Makes total sense. I guess I didn't realize the part about having a strong belief that most of the data is arrived with the watermark notion. So I was just confused a bit. So one of the other things that you talk about in the paper was the different windowing schemes you might use to help define the intervals that you're using to measure these streams of unbounded data. Could you talk a bit about the different options that are available that you might consider using and some of their implications?
So the idea with windowing is it's really grouping records in event time. So trying to co-locate events that happened in some time frame window that associates them together. And there's different ways you can slice and dice time. These are effectively the different types of windowing you might apply. So very common ones, to use the terms we use in Beam at least, fixed windows. So this is essentially, I want a window of every hour or every day, just sort of these constant size windows that just come one after another. And this is useful for, calculating statistics of, seeing what's happening on an hourly basis, seeing what's happening every day, just comparing days, day to day, week to week, stuff like that. A slight variation on that is sliding windows, where you still have windows that have fixed size, but they instead of having one window sort of follow after one another, they slide a little bit and then overlap. So this allows you to have sort of a more incremental view over time of these windows progressing, even though they still have a constant size. And then to get into more complex and interesting types of windowing, one that we really talked about and emphasized in the data flow model paper was sessions. And so the idea with sessions is you're trying to capture bursts of user activity. So it's, with these systems that we build, they're very often, as users interact with them, they do so for some period of time. So maybe they're, to go back to the mobile gaming answer, folks play games for some period of time and then they stop. And when you're trying to understand user engagement, the types of things they do, the types of things that make users want to use your system more, it's useful to look at the things they do within the context of these bursts of activity. And so session windows really try to allow you to take these sets of totally independent events that are just each a record of something happened, and place all those events together in a group that captures this burst of activity.
So is the idea like a session ID, a user ID, some kind of correlation ID that says these things are logically grouped together so you can define that burst?
Yeah, so really it's you group by some key, say user, or maybe you want to see sessions over a team of people, right? So maybe you group by a team ID. So you're grouping by some ID that says, I care about anything that somebody with this ID or some set of users with this ID did. And then you look at the times that those events happened, and you say, I care about them, any events that happened within, say, a minute of each other, I care about. So if you've got, a sequence of events, all of which, are within another event, at most a minute apart, those kind of all start to get grouped together. And then once you hit that kind of last event and then the user puts the phone down, there will be no more events within a minute after that. And so you see, once you hit this gap that's greater than whatever you said you want your gap duration to be, then you say, okay, everything that was close enough together was that session.
That was actually my question. I was trying to understand how you had the bounds, at least the terminal bounds of that session. There is some notion of some time lapse or timeout or something that says that terminates that session.
Yeah, you give an explicit gap duration that says, if you don't see an event for this amount of time, treat that as a session being done.
One of the other big things that I got out of the paper in general was that this notion that we don't necessarily need to treat batch, micro batch, and streaming differently, that we could create a level of abstraction where we could kind of treat them the same. Is that an accurate description of that mentality, that thought process?
Yeah, that was definitely one of the things we were trying to get across.
First off, that's awesome. Now you can use something like Flink or Spark or I guess SAMHSA as well and a variety of other tools. What drove you to go there as well?
Within Google, we had long had independent batch and streaming systems. And having worked on them for years, it was clear that they weren't really that different in what they were doing. I mean, there's certainly are differences, but there were more commonalities than differences. And it seemed silly that we, if you wanted to do batch processing, you wrote it in one way. And if you wanted to do stream processing, you wrote it in another way. And so what we really were aiming to do was just to converge the APIs of the two and make it so that our users could fluidly move between them. Because really they're sort of just two sides of the same coin or two different ways of applying the same thing.
My question, I guess, with that, so when you try to please everybody, you please nobody kind of comment, what does the matrix look like for capabilities when you're going from batch to micro batch to streaming? Do you throw out a lot to be able to get a common API that can work across all three?
No, you really don't have to. The reason it works so well is that from an API perspective, batch is effectively a subset of streaming. So anything, if you have a cleanly defined API for describing a streaming pipeline, that applies entirely to a batch pipeline as well.
It's just the window is whatever you're processing with batch, right?
Windowing is a very natural concept in batch. Folks have done windowing in batch in two ways over time. One is that they've sort of pre-windowed their input data. So say I'm computing daily statistics, they would pre-silo data, records into, a day's worth of data and then process it. That's one way. The other is you do have batch systems where they've built in, sort of custom windowing to say, I've got my batch of data, but I also, within that batch, I'm going to break it down into windowing. So sessions is an example. There are lots of folks that have written custom session windowing code. So that all applies very cleanly. I think the one thing that you tend to not utilize as much in batch is triggers. We haven't talked about triggers yet. We haven't sort of gone through the full Beam model, but what those really are within streaming is a way of declaring when you want your outputs to be materialized. And you don't need this as much in batch because with a batch you just say, well, I want them when you're done processing all the data in the input batch. But when you have sort of an unbounded stream, you need some way of declaring, when do I actually want to see my results? I can't wait until the end of time. What's a reasonable way for me to do it? And there are a handful of very common ways to do it. And then the Beam as it currently exists gives you a massive suite of ways to slice and dice things, which is probably more power than folks need.
We talked about the structure of data, how it's unbounded, how it's infinite. We've talked about this ability to use a common API across multiple paradigms. We've talked about windowing. We've talked about streams, but there's different times when you can use any and all of this. So in this talk that you did in QCon San Francisco last year, you talked about a model for reasoning about when and how to use different capabilities of Beam. Can you talk a bit about that?
So we have this cute little idiom of, what, where, when, how being sort of the four questions that you want to think about when you're writing any data processing pipeline. So the four questions are, what are you calculating? Where in event time are you calculating it? When in processing time do you want to see your results? And how do you want refinements of those results to relate in cases where you're sort of seeing them multiple times? So I'll walk quickly through each of these. And then, anybody that's curious to learn more should, look at the blog posts I wrote or look at the data flow model paper. They both go pretty deep onto this. So the what question is the first one. This is really, am I calculating histograms or sums or machine learning models? This is really kind of what you think of when you think of classic batch processing or the question you're answering there of, when I get some input, what am I calculating? So that's all that question is. The rest of the questions really provide you additional tools for reasoning about time, which is important when you're dealing with these, unbounded, massive, sort of unending data sets that we talked about. The first of those three additional questions is where in event time. We talked about event time and sort of the importance of understanding when data happened specific to the actual action that when it had occurred. And so that's what the where question is. And it's really answered by windowing, which we also discussed. So that's sort of, just where in time do you want to frame the position of these data and analyze them? The next question then is when in processing time do you want to materialize these results? So as the pipeline is processing things, when do you actually want to kick out an answer for the user to see? In classic batch processing, the answer to this implicitly was when I've processed all of the input. But when you have an unbounded set of data, you really need something that isn't just the end of the input. You can't wait forever, right? And so there are a few major options here. I'll touch upon the ones that are most commonly used. The one you see most commonly across systems today is essentially sort of repeated processing time delays. So kind of a consistent cadence of, say, every minute of processing time or every hour. Say you're computing daily statistics. What you would get here is then, as you're grouping records by day and whatever other criteria you've established in computing, your sums or your histograms, every minute you would produce an incremental result sort of saying, here's the value for this given day as of now. And a minute later, you would have accumulated more results and have a new answer. You'd say, okay, well, here's the new answer for that hour or that day rather. And this allows you to build up a view over time of what's happening in that day window without waiting until the end of the day, plus whatever time it takes to process all the data for that day. So you see this in Spark streaming, you see this in Kafka streams. This is a very common thing. It's essentially kind of like, if you're familiar in SQL with the materialized view semantics, where you create a standing query. Those typically are updated with every record, but you can kind of configure it. But that's essentially what you're getting is materialized view semantics. Give me this continually updating view with some possible delay in the cadence of results. Then another type of trigger that we use commonly in Beam is a watermark trigger. And this is essentially when for use cases where you want either a single result for a given window, or you at least want to be able to annotate your results and have some confidence of their completeness. What you can do is you can say, I want to trigger a window when the watermark passes the end of that window. And we talked about watermarks a bit, saying they're kind of a notion of completeness. So what this means when the watermark passes the end of a window then is that the system has some amount of confidence that you've seen all the inputs for that window. And thus, you can think of anything you calculate over that window to be complete. So this is really important in cases where you literally want a single answer. Like you need one answer. You can't have multiple answers. You can't just do continually polling of materialized view kind of updates. You just need the system to give you a single notification, when it's done. That's what this is very good for. Example that I usually cite is like anomaly detection. So if you want a system that is, say the example we had in the Millwall paper was the system called Zeitgeist that performed anomaly detection on Google search queries. So it would build up these statistical models of sort of search query traffic, per query. So, you're searching for, I don't know, earthquakes or something like that. And you can actually see, there's kind of a shape of what people are usually searching for. And it just monitors live traffic and compares that to your models. And it's able to detect when a given search query either spikes, so suddenly way more popular than it used to be, or dips, is much less popular. And when that happens, then you want to give basically one answer saying, hey, I've seen a spike or I've seen a dip. You don't want to continually, be outputting, I don't think there's a dip. I don't think that, I don't see anything. I don't see anything. I don't see anything. And have your downstream system have to, pull this massive database trolling for, notifications. And so really that when question is answered by kind of a combination of triggers and watermarks. And then there's a whole bunch of different ways that you might want to specify triggers, but those are kind of the two main ones. And combining, watermark triggers for completeness and periodic triggers for, regular updates is kind of the main set of patterns that folks use. And then lastly, there's one more question, is how do refinements or results relate? So in those cases, like with the materialized view version, where you're getting multiple outputs for a given window, how do those multiple outputs relate to each other? Do they build upon one another, or are they completely distinct? Are they essentially deltas? So this kind of gives you a way to fine tune your outputs, based off of how you want to consume them.
So no matter what you do when you define these windows, how you define these triggers, eventually you're going to have late arrivals that are outside of that window. What are some of the strategies for dealing with those late arrivals?
There are a few a few options that are common. One is just throw it away. So if in some cases you just don't care. In others, you might want to incorporate those results into new results somehow. So again, if you're doing these periodic materialized view kind of updates, just sort of adding them in and adding them into the next update of results works fine. In some cases, you might want to give the new results and also say, previously I had told you that the answer was 10, now it's 15, take away that 10, sort of give an explicit retraction of the previous answer, which is can be important when the new answer might be processed in a different way than the old answer. And you need to tell the system, actually revert this old answer and then process the new one. Another thing, I think the other main common thing that folks will do is that they will sort of partition into two sets of answers. They'll have kind of the main answers, and then they'll have like a dead letter file that they sort of they either shove the records into explicitly and without not process them, but just have a list of like, these are all the things that showed up late and we can look and see if we cared.
And then you process those independently of the other results.
Yeah, either reprocess them or just keep an eye on them and make sure it doesn't suddenly become huge or miss anything important. So those are, I think, the three main ways that folks use or deal with late data.
In both the paper and the talk, you started off with describing the shape of data. what it looks like today in a typical, I don't know if it's consumer facing, web facing, or just in general, what data tends to look like today. Can you talk a bit about what the shape of data tends to look like in applications today?
Yeah, I think what I was getting at there is really trying to highlight that the vast majority of data sets we use today that we care about, particularly in business, are unbounded data sets. They are essentially infinitely growing, continuous data sets that don't have clear lines of, sort of little finite pools of data. Like, it's really just data keeps coming. So much of the data we process is user-driven data. That isn't to say that's the only thing you care about. I mean, there's still like maps processing, processing maps of the world. This is an important type of data processing, and those often are not, continuously growing unbounded data sets. But a lot of the business-driven use cases care about what users are doing, and these types of user interaction data sets are unbounded, infinite. They just keep coming, and oftentimes they're wildly out of order. This is, if you're, particularly in the case of mobile events, mobile is such a big thing in the world these days. You never know what the delay is going to be between the time when a user actually does something on their phone and you get that event.
In the paper, you specifically say something, and I'm going to misquote, but it was something like that. You have a preference for the term bounded and unbounded over streaming and batch. Why was that?
The main motivation there, I guess there are kind of two motivations. One is that it's just a better characterization of the salient characteristic that's important when we're discussing this. Like, streaming and batch are really terms that describe the type of execution engine that were being used in these cases. But the thing we care about is the data set finite or infinite, essentially? Is it bounded or unbounded? You can process a bounded data set with a streaming system. And you can also process an unbounded data set with a batch system. People have been doing this, I mean, ever since MapReduce was created at Google. It was used to process search queries, which is an unbounded growing data set. It's just you do so in a very ad hoc way of, ahead of time grouping together finite pools of data. And so the hope was to sort of draw clarity to the important characteristics of data itself and separate that from the execution engines. They have their de facto uses for, a given type of data set, but they can be, they don't dictate that you can, process a bounded or unbounded data set.
I want to transition just a bit now about a talk that you're going to do at QCon this November, and it's Streaming SQL Foundations. Why I heart, thank you for using the heart there, that's cool. Streams and tables. In this talk, you talk a bit about kind of the beam model that we've been discussing, and you did a couple of great papers that I really haven't talked much about, but Streaming 101 and 102, people should check that out. If everything we just talked about was interesting, take a look at those. They'll be in the show notes. But then you merge that with some of the stream and table theory that Kleppman and Jay Krebs have talked a bit about in different posts. Can you talk a bit about what you're planning for this talk in San Francisco?
Yeah, so this talk really has two parts to it. The first part is talking about streams and tables, and the second part is talking about how that relates to SQL, and specifically, incorporating streaming into SQL. And it's basically covering two chapters of the book that I'm writing that's coming out soon. So it tries to at least capture kind of the important details, and then, if folks want to go deeper, then they should, look into those chapters and they can kind of learn more. So the first probably 2/3 of the talk really covers the streams and tables stuff. For anybody that's not familiar with this terminology, basically, comes out of the database world. Martin Kleppman and Jay Krebs, as you noted, have kind of talked about this for years. The Kafka community has been talking about it. But the idea is, with a database, you've got database tables, as we're all familiar with. And the way that databases work is, as you're applying transactions to those tables, those transactions come in, they're written to a transaction log, and then that log is serially applied to the tables. Well, that log is essentially a stream. And so they've extracted this sort of conceptual view of things, of having, sort of streams. The application of a stream over time is essentially what yields a table, right? And then the flip side also comes out of databases. If you think about materialized views of how do you go from a table to a stream, well, it's really that same log, but viewing it as a change log from the table. So the sequence of changes that happen to a table is essentially a stream of the updates in that table.
Event sourcing, right? It's each event and then the modification, the CRUD operation of that aggregation of all those events that came through.
Exactly. It's viewing that evolution of the table over time as a stream of these events. And so what I do in the talk is try to, I basically say, this is a cool idea. How does it relate to the beam model that we've been discussing? Because the beam model, talks about, it's got the what, where, when, how stuff. You've got windowing, you've got triggering. Like, how does this all relate? So it tries to explain this in two ways. First of all, it walks you through MapReduce, so sort of classic batch processing as many of us understand it, and shows you how stream and table theory relates to MapReduce. And this is interesting both because it's a relatively simple example, but you can see very clearly the transformations that the data takes from tables to streams and back again throughout, and start to infer properties between them of what is it that really takes you from a stream to a table, and what is it that really takes you from a table to a stream. And it also lets you see this in the context of bounded data, which is maybe a little unintuitive given that you're using this word stream, but it helps highlight that streams can be bounded. It's a way that data operate, but it's not. It doesn't. A stream doesn't capture this unboundedness. It can be bounded. And so then I end up with kind of a basic theory of how streams and tables relate, and then we look at the beam model and kind of walk through the 4 questions, just like I did at QCon last year with that sort of fundamentals of stream processing talk. But we see how it relates to stream and table theory. So you can kind of see that like windowing is very related to tables, and triggers are very related to the creation of streams from tables and things like that. So once we've done those 2 things, then I kind of present a general theory of stream and table relativity, as I call it. That gives you the set of rules for reasoning about streams and tables in the context of supporting robust out-of-order stream processing. So that's the first 2/3 of the talk. And then it's really only the last section that we get into talking about SQL specifically. So then the SQL portion of the talk is trying to figure out what it means to have streaming in SQL. And I mean, this is something that the database community has thought about for decades. They've come up with most of the stuff that we do, quite frankly. So most of what the talk really is trying to present it, sort of similar to, as I said, with the data flow model paper, trying to present it in a clean, cohesive way that makes sense. And the key thing I try to call out is you have SQL, right? And it's built on this relational model, this relational algebra, which is really sort of a mathy way of looking at things and defining all the operations you could
prevent redundancy.
Yeah, all the operations you can do. And so the core data object in relational algebra is a relation, which is sort of effectively what we think of as a table. It's this sort of name type columns and rows of data that sort of give you the relationship of the data to these attributes. And so the point I try to get across in this section is that when you're dealing with streaming, you're really dealing with data over time. And so by extending the core relational object to not just be a sort of point in time snapshot of a relation, but really this thing that we're calling a time varying relation that essentially captures the evolution of that relation over time, you then can apply all of the full suite of relational algebra to these time varying relations and have everything just work out. And that means that you don't really have to change anything in the SQL algebra. It just intuitively makes sense and works in the context of data over time, which means it just works for streams and tables. And then the last 5 minutes of the talk is talking about extensions to SQL for streaming, which I think is what a lot of folks probably expect the talk to be going in. And that really tries to hammer home the point of if you integrate this stuff in cleanly and choose good defaults, you often don't need extensions. And in the cases you do, you can really limit it to a specific subset of things that hopefully isn't too burdensome, sort of conceptually. So I try to explicitly call out kind of the main points that I see as important there. And that's really all we have time for on the talk, because there's quite a lot of information in it.
Yeah, that's definitely a lot. Super interesting. When you talk about not a lot of time to get into, one thing I didn't hear you mention were joins, and that's something that I find super interesting, at least with streams. How do you address when you've got this unbounded data set? How do you join to another stream, to another set of data?
So it's a lot easier to discuss if you've actually seen the talk and kind of have all the terminology I talk about in there.
Of course. Sure.
The core of it, the way I look at it, is that all of your joins at a conceptual level are stream-to-stream joins. People will often talk about stream-to-table joins, but at the end of the day, when you're doing a join, you're joining 2 streams. And there's just different ways of creating those streams and different ways of doing, sort of joining them together. I think the thing that gets really tricky when you're doing joins, a stream-to-stream join at the heart is really just you're sort of grouping those 2 streams together, right? You're accumulating data on some common key, and then as you've accumulated a sufficient amount of data that you have a joined result you care about, you emit a result. So that's relatively straightforward. The interesting part comes when you start talking about temporal joins. So doing joins within the context of event time and getting correctness there. So Julian Hyde, who's the lead engineer on the Apache Calcite project, which is a SQL parser, that's the one that we're using, that Flink's using, et cetera. So he and I have talked a lot about this, and he proposed an example in a document that he wrote of currency conversions. So imagine that you're joining a stream of currency conversion rates. So this is, I want to convert yen to euros. What is the order price at a given point in time? And you're joining that stream with a stream of currency conversion requests. So, here's 500 yen, convert this to euros at this point in time. And both of those streams can be out of order. So you could theoretically get, here's a rate for conversion at noon, and then get an order for 12:05. And at that point in time, you'd say, okay, well, I know my rate at noon was 10 or whatever. Do your conversion, and then later get a late event that shows up and tells you you actually had a different order or a different conversion rate 2 minutes later that should apply to that. So how do you make this all work out and do it cleanly? And so we have a document that we've been kind of hashing all this stuff out amongst our various communities, the Beam and Calcite and Flink and Apex, et cetera, communities. And I kind of go into detail there of, really I think that this boils down to another form of windowing. And we just need a specific, because what you're wanting to do is you're wanting to slice up these currency conversion rates, within specific points in time. And in this case of time, they're in these windows that I call validity windows, which basically means once you get a new currency conversion rate, it's valid until either the end of time or it's later subsumed by another one.
Till it's replaced, right?
Yeah. And what's interesting about these windows is that they can shrink. So you can get a record that goes, and say, here's my rate at noon, and it goes until the end of time.
But something defines it.
Yeah. And that's something like we don't support this in Beam. We support growing windows, merging windows, but we don't support shrinking them. And so this is one of the things I've been kind of saying we should start looking at is I feel like this is a chance to extend our model further and capture, greater generality.
Very nice.
So we've been working on this, and Julian Hyde, like I said, folks in the Flink community, Julian's been very involved. He's the one that came up with the name time-varying relation and things like that. So there's a lot of stuff out there that I give lots of references from the talk. So there's links to sort of, if you want to go deep on this stuff and see what we've actually been thinking, see what the discussions have been.
That's awesome. So in addition to this talk, you are also the track host for the entire streaming track in QCon SF. There's a few other talks there. What's the big picture for the streaming track this year?
There's really two main themes in the streaming track. The first is sort of modern concepts in stream processing, new and exciting things. And then the other is interesting large-scale use cases, doing stuff at massive scale. On the first one, sort of modern stream processing, we have a talk from Matt Zimmer at Netflix, who's going to be talking about custom windowing with Flink. Flink and Beam, I think, are the only two systems out there that I know of that support custom windowing. Most of the others give you kind of 3 or 4 pre-canned things, and that's what you've got. And he's going to be talking about, how they utilize the power of custom windowing with Flink to address their use case, which I think will be really interesting. We've got Stefan Ewan from Data Artisans talking about the future of stateful processing in Flink. I actually don't fully know what this talk is about yet, but I've had him and a couple other folks that I trust who were in the know cite that it's something really cool, and he's been working on it for like 8 or 9 months. So I'm excited to see what it is, and Stefan gives fantastic talks, so it should be good. And then my SQL talk is the other one that's kind of in that part of the sort of theme. And then on the use case talks, we've got Facebook is coming to talk about their streaming systems, and they've built up really cool infrastructure within Facebook that makes it very easy to quickly iterate and launch new pipelines and do so at massive scales. And so I think there'll be a lot of interesting stuff for us to learn from that. And then I've got Vasya is going to be talking about a system called Strymon that she's working on that is essentially trying to optimize data centers. So we're talking, massive scale, sort of optimizing everything within a data center to make them run optimally, which is a big deal for when you're starting to talk about really, massive scale data processing. Very small changes there can have very large ramifications as far as cost.
Well, sir, thank you for taking the time to chat. I'm looking forward to the talk. I'm looking forward to just staying with you on this. I feel like I've been on this journey with you from kind of the paper through the talk and now into streaming. Looking forward to your book. So thank you for taking the time to chat with us.
Yeah, thank you. Appreciate it.